Hello, dear MECH 100 students. As you remember, last meeting time, to the end of the class, focus your attention to Newton's universal gravity law and explain what is G in the famous formula. Yes, weight is equal to m times g. Well, instead of calculating the term in the equation, it is universal gravitational constant times mass of the earth divided by the square of the distance between the center of gravity of the earth and the center of gravity of the object. Again, using the corresponding strange difficult numbers. Well, it is done only one time and determine the result. If it is calculated at the sea level, we obtain the result of this term when we substituted the numbers takes 9.81 meter per second square in SI unit system. And in compact form, we say that the force applied by the earth onto the object, it is denoted with W, capital W. It comes from the first letter of the word, we say weight, is equal to mass of the object times the result of the term, calculated term, g, lowercase g. It is called acceleration, gravitational acceleration. Why it is called acceleration? Although it is not an acceleration term. I explain the reason. In free fall, the number equals to g becomes equal to the acceleration of the motion. So since it is so in such a case, special case, free falling case, it equals to the acceleration of the motion. Conventionally, it is called gravitational acceleration. And then after making such a highlighting, remember, I focused the attention followingly to this notice. Said that balance, not a matter which kind of balance, spring type or one pan digital balance or a famous equal arm type balance. Not a matter which kind of balance, but it is true, balance cannot measure mass. Balance can measure the magnitude of the force applied by the object on its sensing unit. Although it is so, unfortunately, in elementary school, even in high school, teachers say that, yeah, well, using equal arm balance can measure mass. No, cannot. It is wrong. Well, at this point, I want to open a parenthesis and then prove why it is so, why the balance cannot measure mass. To be able to clearly understand my explanation and prove, well, one more nested parenthesis is needed. I want to talk about free body diagrams first. Well, to be able to clearly understand which forces are being applied onto an object, so well, when we edit the forces, whether can find the result as 0 or well, the result is a certain number. If there is the net force applied by the surrounding onto the object is not equal to 0, then this means object will move with an acceleration. So to be able to see the status of an object, well, the thing to do at the beginning is that free body diagram. Draw the free body diagram of the object. What is free body diagram? Well, free body diagram shows the object as being isolated from the universe. Well, after isolating the object from the universe, can find the object as isolated and the rest of the universe. Yes, the rest of the universe is called surroundings and the isolated object is called system. And then free body diagram. It is a schematic view. It shows the outline of the object. Okay, and then we show all the forces applied by the surroundings onto the object, onto the system. Indicate all the forces. In doing this, which kind of force is applied or can be applied by the surroundings, it is important. We should know or consider the kind of connection between the system and its surroundings. Okay, depending on the type of the interaction, connection between the system and its surroundings, can easily say something which kind of force in which direction is applied, can be applied by the surroundings onto the object. Okay. Of course, showing the forces, we use the common notation. To say there is a force over there, we use graphically arrow. Okay, it corresponds to the force applied by the surroundings, and write some letters, label the forces to be able to easily distinguish the force, which force is in consideration, which forces we have, etc. Letters are used to represent magnitude and directions of the forces. Okay. Well, the interaction or the relation, connection between the surroundings and the system is important. Well, in application, objects are connected or be in relationship with their surroundings through the existence of cable, through the existence of a connection, pin joint, pin connection, or there may be roller and some others. Okay. If the connection facility is a piece of cable, neglecting the weight of cable and considering cable as ideally elastic element, we say that whatever the inclination or orientation of cable is, then the force applied by the cable onto the object, the force applied by the surroundings through the existence of cable connection onto the object will be in the same direction. Since cable is elastic element, flexible, perfectly flexible element, it cannot apply, surroundings cannot apply a compression type force, pushing type force. Surrounding through the cable, via the existence of a cable, can apply a pulling force only. Since it is considered as perfectly flexible member, facility, it can only apply a force, surroundings can only apply a force through cable connection or piece of rope connection as pulling type force, and whatever the inclination of the cable or rope is, well, the same with the same inclination. The inclination in this example, inclination of this piece of rope or cable is theta, and the force exerted by the surroundings via the existence of this connection onto the object is pulling type and in the same inclination. So knowing this characteristic of cable connection in drawing free body diagram, after isolating such a part of the object, can put such a force as the force applied by the surroundings onto the object. If the connection between the object and its surroundings is through a weightless link is not weightless, but it is weight with respect to the weight of the others, and the applied magnitude of the applied forces may be negligible. With this assumption, say that it is a weightless link. If the link is a weightless link and it has been connected to the object and to the surroundings at it is both of the ends with frictionless pin connections, then can say that whatever the inclination of the link is, then the force applied by the link onto the object will be in the same inclination. But of course, depending on the case, it may be a pulling force or pushing force. At the beginning, we may not know which one is the case. Solve the equation and then find the direction of the force, whether it is pulling or pushing type. If the connection between the system and its surroundings is through the existence of rolling elements, then the resultant force applied by the surroundings onto the object at such a place through the existence of rollers will be just a force, not pulling but pushing type force, in the direction which is perpendicular to the contact surface. Okay. Yes. If the connection between the surroundings and the part of the object, which is our system in consideration, is through a pin connection, yes, like this, frictionless pin connection, then pin can apply pin connection, through the pin connection, surroundings can apply an inclined force. Cannot set a rotational effect. Moment is out of question. Inclined force, for the convenience, is resolved into its horizontal and vertical components in the XY direction. Okay. Connection is such a one that there is a road and there is a terminal in the structure of the object. Member fixed connected to a collar on smooth road. Smooth road means friction is negligible. Okay, roughness is perfectly zero, so there is no friction force. Well, in such a case, the effect of the surroundings onto the system through the existence of such a collar connection is a force in the perpendicular direction to the axis of the collar and a moment, a couple. Okay. If the connection between the surroundings and the system is such a fixed connection, assume that part of the surroundings is a wall and the terminal of the object has been rigidly connected to the wall. Then the effect of surroundings at such a connection onto the object at this terminal will be an inclined force and also a couple. Okay. Yes, we know the characteristic of the connection and the corresponding effect of the surroundings through the existence of such a connection. Then, when after isolating the object from the universe, drawing its schematic figure, we can easily show the forces and couples at the terminals of the object where there is an interaction between the object and its surroundings. Weight of an object. Weight vector is representative vector. It is the resultant of all the gravity forces applied by the Earth onto each particle of the object. Considering the radius of the Earth is a very long distance between the center of the Earth and the center of the object in consideration, in the vicinity of the object can consider the gravity forces applied by the Earth onto each of the particles as parallel to each other. The resultant of such a parallel force system finds its point of application at a certain special location. That location is called center of gravity. Center of gravity. Representative weight vector, the resultant of the gravity vectors, is located at that special point of application of this representative vector. Weight vector is center of gravity. If the material has homogeneously been distributed, uniformly distributed, then center of gravity and center of the volume coincides. Geometric center or centroid and center of gravity will coincide onto each other. Okay. Close the nested parentheses and then see some examples. For instance, here, part of the universe, we have ground, a wall, stairs, and a person just stepping on, rising up. Well, say that our purpose is to make an analysis while the person just climbing over, stepping on the ladder, steps of the ladders, whether the ladder going to be in equilibrium or will move. Well, say that it is the problem, it is the issue. Isolate ladder from the universe. Yes. Show it schematically, and then depending on the type of connections, interaction between the object and its surroundings at the terminal parts, show the forces. If there exist, of course, show the couples. Now in this example, the wall, surface of the wall and the contacting surface of the ladder are both perfectly polished. It is an assumption, so there is no friction. Since there is no friction, wall can exert just a force onto the ladder in the perpendicular direction with respect to its surface. Okay. This force is the force exerted by the surroundings onto the stairs through the existence of this person. This man is a part of surroundings, and it is stepping on, that person stepping on one of the steps and applying such a force. This is the force applied by the man onto the stairs. Okay, it is in the direction toward the center of the earth. Okay, this force is the weight of the representative force. It corresponds to the weight of the ladder, and the surface of the floor is a rough surface, so we have not only normally directed force but also tangentially directed. Tangential component is the friction force, and the other component is the normally directed one. Yes, in this example, these are the forces applied by the surroundings onto this system. System in this example is the stairs. Another example, there is an inclined and roller rope mechanism. There is a weight over here. There is an object connected to one end of the rope cable, and at the other end we have another object. It is over an incline in contact with its surface. If the purpose is to see whether this block, which is over the incline, is in equilibrium or gonna move with an acceleration, well, for that purpose, isolate this box from the universe, say that it is the system, and draw the free body diagram. This figure, my cursor is moving around it, is the free body diagram of this box. This is the weight of the representative gravity force. It is at the center of gravity of the box, and its magnitude is equal to mass times g. Okay, since this is a cable connection, through cable connection, surroundings can apply tension type force. Whatever the orientation of the cable is, the inclination orientation of the force will be the same. This is the force applied by the cable. Okay, and then what about the rest? If the surface is frictionless, then this component will be zero, only normally directed force. But if there is a considerable frictional effect at the mating surface, then say that we have such a force, okay, in the tangential direction. This is friction force, and this is the normally directed component of the force which is applied by the surface of the platform, surface of the incline. And then, well, solve the equation, and then see, adding the forces up, see whether the result is zero, if not equal to zero, and then determine the acceleration or deceleration. If the issue is to deal with the equilibrium or the motion of the other box, then yes, define it as the system. Here it is the free body diagram, isolated from the universe, and then show it schematically with the forces applied by the universe. Well, the universe surroundings applies the gravity force. Okay, Earth is a part of the universe, and the Earth applies such a force. The magnitude of the force is m times g, and the other force is the force applied by the flexible cable. Since the cable is vertical, this force is vertical. Since it is a cable, cannot exert a pushing force, can only apply tension force. Here you see it is a tension force. And then considering this free body diagram, add the forces up, and then see whether result is zero. If it is zero, then say it is in equilibrium. If not, then this block will be in a displacement with a acceleration. Newton's second law will be the governing mathematical expression of Newton's second law will be the governing equation in such a case. Yes, and then see some other examples. There is a pulley, and in the rim of the pulley we have cables. Okay, and then, well, surroundings may exert such a tension force at the end of this cable, another tension force at the other end of the cable. Okay, if in the rim of the pulley the friction is negligible, then the tension at this end will be equal to the tension at the other end. Another example, there is a winch here. The bucket is held in equilibrium by the cable. This is the bucket. Okay, and this is the force applied by the cable applied by the surroundings of this system through the existence of this cable connection, and the other force is the weight of the object, the resultant of the gravity forces. This is the free body diagram for the bucket. Another example, there is a beam here. It has been partially shown. Beam and its surroundings, you see, are in such a connection. There is a roller, okay, between the surroundings and the system. In other words, at the terminal, this connection part, we have a roller, frictionless roller. If there is a roller, then surroundings can apply a force in the radial direction. In the radial direction of the roller can apply such a force. Cannot apply tension force. Roller can apply, since it has not been rigidly connected. There is a roller and beam is just over the roller. So roller cannot apply tension force, can apply pushing force. And in which direction? At the contact point, see the radial direction, line of action of the force just extends to the center of the roller, okay? So radially directed force. If there is a pin connection, then through the pin connection, surroundings can exert an inclined force. It may be pushing or pulling type. And fixed connection, you see here at the terminal connection part, when we isolated the beam from the rest of the universe, at the terminal can have an inclined force applied by the surroundings through the existence of this fixed connection and a couple. Yes, free body diagrams. Another example you may study. There is a roller type joint. This is a pin joint. Okay, there is a cable connection here to this hinge ring. A cable has been connected, and to the cable connection a force is being applied. There is an inclined force applied by the surroundings at this point of the beam. Okay, well, draw the free body diagram of the beam. Okay, inclined force can be resolved into its horizontal, vertical components. The through the existence of roller type joint here, surroundings can apply a force in the radial direction. Okay, and this is a pin connection, so can have an inclined force applied by the surroundings onto the object at the point, resolve its components, and then the rest is just the evaluation part. Add the forces up and then see whether the result is 0. If you don't know the magnitude of some of the forces, then write the equation. Of course, if you know that it is in equilibrium or if you know that it is in acceleration, write respectively either Newton's first law equilibrium equation, sum of the forces 0, sum of the rotational effects moments 0. or if it is in motion, then using the second law of Newton's second law, be able to write the governing equation and then solve the equation to determine the unknowns. Okay. And then, well, close the parenthesis. After talking about the types of joints commonly used between the surroundings and the system, and the corresponding forces applied by the surroundings through the existence of such terminals. And then I think sufficiently managed to answer the question, what is free body diagram? Then close the parenthesis. And then continue. Well, say that this is my purpose is to prove that balance cannot measure weight, cannot measure mass. It can measure the force applied by the object onto its sensing unit. First example, there is a spring type balance. Okay, if this spring is a Newtonian spring, then between the elongation of the spring when it is stretched and the magnitude of the force applied to the terminal of the spring are proportional, linearly proportional. The proportionality constant is called spring constant. Well, as it is written here, the force applied to the terminal of the end of the spring is equal to spring constant times the elongation of the spring under the action of the applied force. Okay, now say that we have an object. It has been hanged to the terminal of the spring type balance. Okay, the object is just stretching the spring, and there is a scale to measure the elongation term delta L. Object has not been connected. See the initial position of the needle along the scale, and then hang the object, and then see the displacement of the needle. It is at the terminal point of the spring. Say this linear elongation in this formula is delta L. Draw the free body diagram of the object. It is, our purpose is to measure its weight, measure its mass, weight. Let's say, although mass cannot be measured using a balance, say that it is the purpose. After isolating the object from its universe, yes, schematically show it. This rectangle corresponds to the object. Surroundings of the object applies the gravity force, representative gravity force. It is just at the center of gravity of the object. Point of application of the resultant gravity force is at the center of gravity, and this is the point of application of the force applied by the spring onto the object. F sub spring is the force exerted by the spring onto the object. In figure C, we have the free body diagram of the spring. Well, at the connection point, this point, the force applied onto the object by the surroundings through the spring, and in this free body diagram, the force exerted by the object onto the terminal of the spring are action-reaction pairs. So the force exerted by the spring to its magnitude is equal to the force exerted by the object at the point. This is action, this is reaction, or vice versa. So the force exerted by the object is equal to the force exerted by the spring. If you write the equilibrium, if you write the equation, since it is not moving, it is not accelerating under static conditions, can say that sum of the forces for the free body diagram in figure B is equal to 0. So force exerted by the spring onto the object minus the gravity force equals to 0. From here can see that the force exerted by the spring is equal to the weight of the object. And spring force exerted by the spring is equal to the force exerted onto the spring by the object. So the magnitude of this force is equal to the weight of the object. Okay, at the other terminal point of the spring, well, we have the force exerted by the surroundings onto the spring at terminal point A. If we neglect the effect, if we neglect the weight of spring, it's a little object, and relative to the weight of the object, it is a massive big object relative to the size of the spring, can neglect the weight of spring. So, well, for this free body diagram, since spring is not moving, not accelerating, can write the equilibrium equation and say that the force at this terminal point is equal to the force at the other terminal point. Okay, so the force at the terminal point of the spring is equal to spring constants times the value of the elongation, stretch value. From here, write this expression. Elongation term is equal to the force at the terminal point divided by spring constant. Since this force is equal to the weight of the object, then from here can find that the elongation term delta L is equal to weight of the object divided by spring constant. Okay, this scale you see shows actually the elongation value, stretch value, and it is not equal to the mass. The stretch, it is the indicated value, corresponds to mass of the object times g divided by k. Of course, delta L elongation terms, just using this formula, can be calibrated, and along the scale the corresponding mass values or weight values can be written. If the balance is under static conditions, loading, then yes, can say that delta L is proportional with the weight of the object. Calibrating the scale can thereafter use this spring type balance to measure weight. Okay, but how about dynamic loading? Say that while we're balancing the object to measure its weight, let's say, as a whole, spring and the object just in motion. Okay, well, if the object, whatever it is not stationary or not moving with a constant speed, but it is accelerating or decelerating, then this means the object is under the action of a net force. Newton's second law for a particle or for an object, its size relative to the rest of universe is negligible. The Newton's second law can be expressed in this form. Net force applied by the surroundings of the object is equal to mass of the object times the acceleration of its center of gravity point. A sub g object is the acceleration of the center of gravity point while the object is moving dynamically. This is the governing equation. And then now for free body diagram in figure B, write the equation. Cannot say sum of the forces is equal to 0, so cannot say that the spring force applied by the spring is equal to the force applied by the earth. Here the force applied by the spring minus weight of the object is the net force, and this term is equal to mass of the object times the acceleration of the center of gravity point. Yes, net force is equal to m times a. So, well, from this governing equation can derive the spring, the force exerted by the spring onto the object. It is equal to weight of the object plus m times a. Okay. The force applied by the spring is equal to force applied by the object. Action, reaction. So, well, for the free body diagram shown in figure C, in this case, well, the spring type balance and the object, both of them are moving, accelerating. Write the equation. Fa is the force at the other terminal point is equal to the force at one of the terminal of the spring plus mass of the spring times the acceleration for the center of gravity of the spring. Fa minus F object is the net force exerted by the surroundings onto the system. Here in free body diagram C, system is the spring. If we neglect the effect of the gravity on the spring, weight of the spring, yes, assume that weight of the spring is almost 0. Then, well, approximately from this spring characteristic equation of the spring can write, well, delta L is equal to F object divided by K. F object is equal to F spring. It is equal to weight of the object plus mass of the object times acceleration. And then you see elongation term, the stretch of the spring is not equal to weight divided by spring constant. It is equal to weight of the object plus this term. Although it is so, how we can say that such a balance can measure weight, can measure mass? If acceleration is 0, can say that we can use it to measure weight, and thereafter dividing weight by the gravitational acceleration, then indirectly determine mass. But this instrument cannot directly indicate the value of weight if the loading is dynamic. Similarly, while drawing the free body diagrams of equal arm free body diagrams of the object and standard weight, it can be proven that even equal arm scale cannot measure weight, cannot measure mass. If the measurement is held in atmospheric air, since the density of air is a small number, the buoyancy force, effect of buoyancy can be neglected. It's an assumption, and when we neglect the effect of buoyancy, of course can measure the weight of the object approximately. But here say that this measurement is in an environment, its density is not very small. For instance, ambient is water. Density of atmospheric air is 1 kilogram per cubic meter, but the density of water 1000 kilogram per cubic meter, 1000 times greater. Say that the object is a block. It is made of a light material, for instance styrofoam, and in using equal arm scale balance, we use standard weights. Onto one of the pen put the object, onto the other pen put the standard weight, and seeing that the arm is in equilibrium and horizontal oriented, can say that if the buoyancy force is neglected, of course, whatever the weight of the standard object is, then the weight of the object is equal, the same. Because since the beam is horizontal oriented, this means the rotational effect of the force exerted by the standard weight onto the pen is equal to the rotational effect of the force exerted by the object. From this equilibrium equation, can conclude that weight of the standard weight is equal to the weight of the object. But if the buoyancy force is neglected, now say that buoyancy force is not so negligible. Free body diagram for, in this example, styrofoam block. The representative weight vector is at the center of gravity. Assume that material has been uniformly distributed and center of gravity and center of volume are coinciding. Capital C to say centroid, center of volume. Well, the force exerted by the pen of the equal arm scale is at the bottom surface, and I denoted this force using this index. Pen, force exerted by the pen at C, pen C, through the existence of pen C, surroundings can exert such a force onto the styrofoam block. This is the force exerted by dirt, resultant force exerted by dirt, weight of object, and the other force is the buoyancy force. The buoyancy force passes through the center of the volume, centroid, okay, and its magnitude is equal to density of the surrounding fluid times volume of the object times gravitational acceleration. Okay, equilibrium equation. From this free body diagram can write the expression that force exerted by the pen C is equal to weight of the object minus buoyancy force. In other words, this force plus the buoyancy force is equal to the weight of the object. Free body diagram for the standard weight. Similarly, weight of the standard weight, okay, it is at the center of gravity of the weight. Buoyancy force, volume of the standard weight times density of the surrounding fluid times gravitational acceleration is the magnitude of buoyancy force, okay, and this is the force exerted by the surroundings onto the standard weight through the existence of pen D, F pen D. Say that it is the case relative to the volume of the object, the volume of this dense standard weight is negligible. Okay, neglecting the effect of buoyancy force, since the volume is very little, can neglect the buoyancy force, comparing with the magnitude of this force with the buoyancy force exerted by the surrounding fluid onto the other object, onto the styrofoam block. After neglecting the buoyancy force exerted by the surrounding fluid onto the standard weight, well, can obtain this equation. Weight of the object, styrofoam block, is equal to weight of the standard weight plus this term. Plus this term. Well, take a highlighter and then see this term. Yes, this is the effect of buoyancy. If the density of surrounding fluid is very small, then this term may be correspondingly very small term, and can say that while using equal arm scale, we can measure the weight of the object just by considering using the standard weights. Whatever the standard weight is equal to, whatever the standard weight is, it is equal to the weight of the object. But if we neglect this term, if we omit this term, if this term is not so small, not negligible relative to the weight of the object and the weight of the standard weight, then of course cannot say that even equal arm scale cannot measure weight. Okay? Weight of object, although balance is in equilibrium, this arm is horizontally oriented, okay, and the weight of the standard weight and the weight of the object just seems as in balance, but it is not. We have buoyancy forces and cannot neglect the buoyancy force. So we must consider this additional term, just making such an experiment and seeing the weight of standard weight, then adding this term can determine the weight of the object. So this example also to prove that even using equal arm scales cannot directly measure weight of something. Okay? Don't forget, scale balance can sense the magnitude of the force applied onto its pen, onto its sensor. And the force exerted by the styrofoam block is not equal to the weight of the block. We have the effect of buoyancy. Okay. Yes. Now have a break and then continue.